with the afternoon with a talk by Sharrock from UCL.
Thanks. Great, thanks very much, and thanks to the organisers for the invitation. So yeah, I'm going to be talking today about a kind of line of work on performing optimization over the space of probability measures in a way which is learning rate free, which I'll try and clarify some of that terminology as we go through the talk. Just a brief outline of what the talk is going to look like. So I'm going to start with some background, some motivation. A central theme of this talk is going to be the connection between kind of optimization on Euclidean spaces and optimization on measure spaces. And so we're going to kind of go through a brief recap on optimization methods on Euclidean spaces, then move on to the Wasserstein space, show some numerics, and then draw things to a close. So a bit of background and motivation. The starting point and a central theme of this talk is that many problems in stats and machine learning can be viewed in some sense as optimization problems over a space of probability measures. And this is a viewpoint which has been around for some time, going back to kind of the 90s, but actually it's found kind of a renaissance in the last 10 years or so. I think it's a really powerful viewpoint and one which still can be exploited more in this community. Okay, so we're going to go through a few examples of problems which can be viewed in this framework. So the first one, and the one which is going to be kind of central to this talk, is sampling. So this is a classic problem: generate samples from some target probability distribution pi, given some information about that target. And we have two common scenarios. So the first, which is kind of the classical setting of approximate Bayesian computation, is that we know the density of the target, but we only know up to some intractable normalizing constant. And the second, which is kind of more the setting in, say, generative modeling, is that we have access to samples from the target, but we don't have an unnormalized density. I'm going to focus mainly on the first of these scenarios, which, as I said, is the standard setting for kind of approximate Bayesian computation. So as I say, this sampling problem can be viewed as an optimization problem over some space of probability measures. So in particular, according to this viewpoint, we're going to view the target pi as the minimizer of some, we're going to call a dissimilarity functional, which is uniquely minimized at our target pi. So in some sense, this is kind of a synthetic optimization problem in that we construct an objective functional whose solution we know in advance, but this is going to be kind of a powerful viewpoint in terms of constructing algorithms and kind of analyzing their properties. And the canonical choice of our dissimilarity functional is going to be the KL divergence, forward KL divergence between mu and pi, which we know is always non-negative and is equal to 0 precisely when mu is equal to the target pi. Okay, so as kind of a subclass of the sampling problem, we have kind of the Bayesian sampling problem, which is, I won't labor this, generate samples from some posterior given some observed data, right? So we have some data set, say with some features W and labels I. We're going to assume some underlying model for our data, parameterized by the parameter we're interested in. Here we've just got kind of a normal distribution. Going to assume some prior distribution as well for our parameter. Again, a very simple example here. And then by Bayes' rule, we're going to get out our posterior distribution. And in particular, this is precisely of the form I talked about earlier, where we have our some target distribution whose density we know up to some intractable normalizing constant. And so going back to the kind of framework, the formulation we had before, naturally, given that here's kind of a sub-example of the kind of general sampling problem, we can, of course, view this, again, as an optimization problem over the space of probability measures. And in particular, and we've seen this kind of formulation before, particularly in Jeremias's talks, we can kind of view pi as the solution of this minimization problem. And of course, there are various extensions and kind of, we've heard a lot about kind of this generalized Bayesian inference framework where we can kind of play around with this, use different loss functions, etc., different regularizers, and we get different optimization problems where we'll end up with kind of a different measure as the solution, which will be some kind of generalized posterior. Okay, so that's kind of example number one. I'm just going to mention a couple of other examples which also fit within this framework and for which some of the tools I'm going to talk about later in the talk can also be applied. So example number two is kind of inference and learning in latent variable models. So a latent variable model, kind of generically speaking, is of the form p theta xy, right? So we have some model parameterized by theta, which relates some latent variables x and some observed data y. And what we'd like to do is learn the parameters of this model and then infer the distribution over the latent variables. So one way we can approach this problem is using kind of the empirical Bayes paradigm. So in this paradigm, we're going to kind of treat theta as a fixed parameter. So we're not going to be fully Bayesian about this. And we're going to try and learn theta by maximizing the marginal likelihood of the data. And then once we've found this kind of marginal maximum likelihood estimate, we're going to perform an inference by using the corresponding posterior. So the classical approach to this, of course, is the EM algorithm. This goes back a very long time. But a very interesting perspective on this problem, which actually, again, dates back to the 90s, but has been revisited in a series of papers in the last couple of years, is that you can actually view this problem as the minimization of a free energy functional. So this looks quite like the KL divergence between mu and p theta, but it's actually equal to the, given p theta is a joint distribution over x and y, actually, when you kind of expand things out, you actually see that this is equal to the KL divergence between mu and the posterior of x given y, evaluated at theta, minus the minus the marginal log likelihood of the data. And once you kind of expand f out in this way, you can show very straightforwardly that for every theta in kind of your space of thetas, the posterior, evaluated at theta, uniquely minimizes the function which takes mu to f theta of mu. And also that the likelihood p theta of y has a maximum at theta star if and only if this functional has a minimum at theta star p theta star. So in other words, we can kind of take this, this inference and learning problem for latent variable models, and we can view it as the minimization of this free energy function. Okay, so one final example, and that is training energy-based models. So energy-based models is essentially a particular class of generative model, right? So in this setting, we are in this setting where we have some IID samples from some data distribution, and we'd like to learn some model of the form e to the minus e theta of x over some normalizing constant, such that our model approximates the data distribution. So what's the way we go about doing this? Well, the standard approach for doing this is to try and maximize the expected log likelihood. Now, the problem with this is this requires sampling from our model, which isn't easy. And why do we need to sample from p theta to maximize this thing? Well, if you take the gradient of this objective function, do a little bit of maths, you end up with this form, and in other words, you have some expectation with respect to your model. So a standard approach to solving this is to kind of alternate gradient steps with respect to theta, and then run kind of one or more MCMC steps with respect to your model p theta. But one, that's kind of difficult to analyze in practice, and two, you might need to run a vast number of MCMC steps to get kind of an accurate sample from p theta. Okay, so how does this fit into this framework? Well, you can actually reformulate this as a min-max problem of the following form. So if we define this objective functional, and this is sometimes kind of referred to as the contrastive divergence approach to training energy-based models. So this is the difference between the KL divergence between mu and the model, and the KL divergence between the data distribution and the model. And it turns out that you can equivalently formulate this problem of learning the energy-based model as trying to solve this optimization problem. So how do we see this? Well, if you fix theta and kind of stare hard enough at this thing, then you can see that p theta uniquely minimizes this, right? The second term in particular is independent of mu, so clearly this thing is minimized by the minimizer of the KL divergence between mu and p theta, which is precisely p theta. And then plugging that back in, you can kind of see the expected log likelihood has a maximum at theta star if the kind of function from theta to f of p theta has a maximum at theta star. In other words, solving this kind of min-max problem is equivalent to solving the original problem we had. Okay, so there are various other examples which fit within the framework, don't really have time to go into them, but essentially the kind of point I'm trying to labour, and have probably already laboured, is that lots of different problems can fit within this framework, and it might be interesting to kind of view them in this way. Okay, so why is this viewpoint useful? Well, firstly, it kind of means we can view these things through the lens of optimization, and in that sense we can kind of take existing established tools from the optimization literature and try and apply them or adapt them to come up with new sampling algorithms. So in particular, you can actually view many existing algorithms as gradient flows over a space of probability measures. So kind of the most famous example of this is Langevin dynamics, or its discretized form, the unadjusted Langevin algorithm. And back in the 90s, it was showed that kind of the Langevin diffusion essentially corresponds to the gradient flow of the KL divergence over this Wasserstein space of probability measures. And there's a whole bunch of other algorithms which can also kind of be viewed through this framework. Okay, so getting on to kind of the more specific point of this talk is that one common feature of these algorithms is that typically you need to set appropriately some kind of step size or learning rate, right? So if you're going to define an algorithm as a gradient flow, naturally when you run this thing on your computer, unless you're working with very simple models, you're going to have to discretize in time. And that means naturally you're going to have to set some kind of learning rate or step size. Naturally you need gamma to be small enough to ensure that your method converges to the target, but you also don't want it to be too small such that you're kind of waiting forever to converge. Okay, and so just as a very kind of simple demonstration of this, this shows a particular algorithm, Stein variational gradient descent, which I'm sure many people will be familiar with. This essentially evolves kind of a set of interacting particles according to kind of a particular form of gradient descent on a space of probability measures. And you can see essentially what you would expect, which is that the choice of step size or learning rate has a very significant impact on the convergence properties of your method. So in particular, you set your learning rate too small, you're kind of waiting for a really long time. You go too big, the kind of whole algorithm explodes, you don't get anything sensible. And you set this thing just right, well, you get good samples and you get them in reasonable time. But clearly this hyperparameter has kind of an outsized impact on how well your sampling algorithm is going to perform. Okay, so how can we tackle this problem? Well, in theory, you can derive kind of non-asymptotic convergence rates for a lot of these algorithms, and by kind of minimizing those convergence rates with respect to the step size parameter, you can in theory find some kind of optimal step size or learning rate for these algorithms. Okay, so what's the problem with that? Well, in practice, typically these convergence results depend on quantities such as kind of the Wasserstein distance between the initial measure and the target measure. And that's something which you can't compute in practice, and so you can't actually compute this optimal learning rate. So that kind of led to this question, which is, can we obtain kind of gradient-based algorithms for these type of problems, so sampling problems and these other extensions I've talked about, which are entirely learning rate free? And again, learning rate I'm using here interchangeably with step size. And the answer to this is yes, otherwise the rest of this talk would be rather short. And this is just kind of a preview of where we're going to end up at the end of this talk. So on the left-hand side is one called coin SVGD, which is this kind of learning rate free algorithm we're going to end up with. And on the kind of three right-hand plots are the ones we had before. So this coin algorithm is entirely learning rate free. And we can see the convergence to the target is kind of at a very similar rate to an optimally tuned version of this SVGD kind of algorithm, which was obtained as a discretization of a gradient flow. Okay, so as I say, the key here really is going to be using this connection between optimization and sampling to develop this algorithm. And so to do that, we're going to start by recapping some basics on optimization in Euclidean spaces. Okay, so this is going to be our optimization problem, and we're going to focus for this talk on convex optimization problems. Things get much, much trickier, of course, when you go to the non-convex setting, so we're going to focus on this convex setting. So here's our problem. How do we solve this thing? Well, in general, we can solve this problem using the gradient flow of f, right? And here I've just given a slightly more general form than what you might be used to, which is, in particular, differential inclusion, where the right-hand side allows us basically to work with functions which are not differentiable everywhere. So this kind of partial f of x denotes the set of subgradients of f at x. And as I say, this means that we can still apply this gradient flow when we have, say, a function like the absolute value of x minus 10, say. And this thing obviously isn't differentiable at a point, but you can always define these subgradients for convex functions. So some basic results. You can show that this inclusion admits a unique, absolutely continuous solution for almost all t greater than 0. And you can also show that the function from t to f of xt is decreasing. And so in particular, the limit of f of xt as t goes to infinity is indeed the infimum of our function. So this is doing something sensible. Of course, in practice, when we run this thing on a computer, when we want to actually use this thing for practical problems, we have to discretize in time. So there's lots of different ways we can go about this. Here are just a couple. Backward Euler, which gives us the so-called proximal point algorithm. And this tends to be a bit more kind of stable than kind of the standard forward method, but it does require us to solve this kind of minimization problem at each step. And then forward Euler, which is kind of the standard algorithm everyone is used to, which leads to this subgradient descent algorithm, or in the case that f is differentiable, this is just our standard gradient descent algorithm. As I've said already, the convergence rate of these algorithms depends on the choice of learning rate or step size. And in particular, the optimal choice of learning rate in this Euclidean setting depends on the unknown distance between our initial point x0 and the optimizer x star. So we can't compute this in practice because, of course, x star is the thing we're trying to find in the first place. Okay, so I'm going to take a brief detour now and talk about another method from the optimization literature, which essentially removes the need for learning rates or step sizes entirely. Now, this is a very different kind of construction to gradient descent type algorithms. I'm going to ask you kind of to forget essentially all kind of intuition about gradient descent type algorithms. This is going to be a very different kind of beast entirely. Okay, so we're going to start by considering this scenario, which for the time being might not seem connected to our optimization problem, but we'll kind of draw that connection in a moment. So we're going to have this gambler, a gambler with some initial wealth W0, and he's going to bet on a series of adversarial coin flips. And the aim of this gambler is basically he wants to make as much money as possible. So in particular, we're going to say in the teeth round, he's going to bet an amount of money xt on the outcome of a coin flip ct. So we're going to just use -1 for tails and 1 for heads. So in particular, the magnitude of xt is going to kind of denote the amount that this gambler is betting, and the sign of xt, so whether it's positive or negative, is going to denote whether he's betting on heads or tails. Okay, so that's the setup. So we can write down the wealth of the gambler, and this is going to accumulate in this fashion. So it's just going to be the initial wealth plus kind of the product of the outcomes and the amount he bets each time. Okay, and we're going to make one final assumption, which is that the amount that the gambler bets is going to be equal to some fraction of his wealth at the previous time step. So the interpretation of this is that basically he can't bet more money than he has. Okay, so that's kind of our setup. So now the question is, how should we choose this betting fraction? Well, there's a number of different scenarios. So if we're in kind of stochastic setting where these are IID coin flips and there's a particular probability, fixed probability of heads, then you can actually show that the optimal strategy is given by this, which is essentially the expectation of the outcome. And this makes sense, right? So if, say, for example, the probability P of getting a heads was 1, so if this was always heads, this tells us that beta T would be equal to, well, 2 times 1 minus 1, so 1. So in other words, we always bet all of our wealth on heads at each time step. That makes sense, right? Because we know essentially in that scenario we're going to always see a head, so we might as well keep betting all our money on heads. Okay, so that's in kind of this simple IID setting. In the non-stochastic setting, so let's now imagine we're in some kind of adversarial setting where, well, actually we're not in the adversarial setting yet, but if somehow these sequence of coin flips were predetermined but non-stochastic, but if we knew them in advance, then it turns out the optimal fixed strategy is given by this, which is essentially kind of the empirical average of the outcomes. Of course, this is, again, a bit unrealistic because we're typically not going to know the future outcomes. So what if we don't know the future outcomes? In this case, we can use this kind of KT strategy, this Krzyzewski-Trofanov strategy. And that is given by this kind of running average of the observations we've seen so far. And so substituting this back into our kind of update equation from before, this yields the following sequence of bets. Okay, so it turns out you can actually show that using this betting strategy, you can guarantee that your wealth will grow exponentially as a function of the sum of the outcomes squared. Okay, so this might seem a bit surprising, but of course, if you think about kind of the kind of strange pathological cases where, for example, you get a heads and then you get a tails and so on and so forth. If for example the sum of the outcomes is equal to 0, clearly this thing doesn't actually grow exponentially. So it's exponentially as a function of the sum of the outcomes squared. And in fact, in this paper from 2016, it was shown that this actually holds for continuous outcomes between -1 and 1, and not just for outcomes either being -1 and 1. Okay, so here's all well and good, but what's the connection between this kind of strange betting paradigm and convex optimization? Well, it turns out that if you construct a betting game where the outcomes of this experiment, what we were previously thinking of as coin flips, are equal to the negative gradient of the function we want to optimize, you can actually show that the average of the bets converges to the minimizer at a rate determined by the betting strategy. Now this is kind of remarkable, and I'm not sure I can give you much intuition for this. This is really something that comes out of the theory. But this is quite a remarkable result because we now have an algorithm which essentially has no dependence on kind of a step size parameter. We have this W0, which is the initial wealth, but essentially it's not very sensitive at all to the choice of that W0. Okay, so where does this result come from? Well, the very nice thing is actually the main steps of the proof of this result are very straightforward. So I'm just going to run through them very quickly. This is, of course, hiding some details, in particular in the last step, but it's kind of instructive to see how we get this result. Okay, so this is the thing we want to bound. This is f evaluated at the average of the bets minus f evaluated at the minimizer. Okay, so using Jensen's inequality, we can bound this by 1 over t times the sum of the differences at each time step. We can now use convexity to bound this above by this thing. Remember here, ct were the negative gradient of our function f, evaluated at xt. So that's just using kind of the that particular first order characterization of convexity. Next, we use the bound we had on the wealth from before. So if you recall, we had this a few slides back, we had this kind of lower bound on the wealth. And so substituting that in, we get the next line. Next, we can kind of take the maximum over the sum of the CTs, and that just gives us that line. And then finally, if we kind of stare hard enough at this thing, this inner term is essentially the definition of the convex conjugate, H star. So H star here is the convex conjugate of H. And so we end up with this bound. So of course, there's hiding some details here because so far we haven't said anything about H star. But essentially what we showed is if we can bound H star, and it has some appropriate dependence on that bound in T, then we're going to have a kind of convergence rate for the average of our bets. Okay, and it turns out, again, and this is a lot of the hard work, which we're not going to go into, and again, this comes from this paper from 2016, it turns out you can find a bound for this H star, and the H star, the bound for that essentially grows as root T. So in particular, when you substitute back into our previous bound, you get the whole bound essentially grows as 1 over root T, plus this additional log term. Okay, so that's nice. So that shows essentially that we have convergence of the average of the bets to our minimizer, and the rate essentially is 1 over root T up to this logarithmic factor. And we can actually compare this with the convergence rate of subgradient descent with the optimal but unknown learning rate. So as I said before, the optimal learning rate essentially depends on the distance between the initial point and the minimizer, and you can show that if you do use that optimal learning rate, you get this kind of convergence rate. So essentially, what is this saying at a kind of a high level? This is saying somehow the price you pay for this algorithm, which is in some sense learning rate free, is this additional logarithmic term in the convergence rate. But of course, this means you don't have to do any kind of step size or learning rate tuning. Okay, so just to try and give a little bit of intuition for how this thing works, I'm just going to run through what the algorithm looks like in a very simple example. So here we're trying to minimize the function absolute value of x minus 10. So the minimizer is at, of course, the point x equals 10. Okay, so we're going to set the initial wealth as 1. And let's look at what all the quantities in the algorithm update look like. So the first thing we're going to do is calculate the betting fraction. So in the first round, if you remember, the betting fraction was the sum of the previous observations divided by t. Thus far, we haven't observed anything. So our betting fraction is equal to 0. So that means, of course, our initial bet is equal to 0. So in the first round, we're essentially not going to do anything, and that is the point plotted up there. So 0. Okay, so now we observe an outcome. And remember, the outcome in our kind of betting experiment here is the negative gradient of the objective function at the current point. So in this case, the negative gradient, of course, is equal to 1. So we can calculate the new wealth. So our current wealth is 1. If we multiply our current bet by the outcome we've just observed, well, that doesn't give us anything more. So our new wealth is still 1. And we can now calculate a new betting fraction. So again, the betting fraction is equal to the sum of the previous observations divided by the number of time steps. So in this case, we've observed a 1, and we've had 2 time steps, so our new betting fraction is a half. So now we make our new bet, which is equal to a half times 1, so a half. And again, that's what's shown on the slide. So again, we can carry on playing this game, right? So the next outcome we see is, again, a 1, because the gradient is still negative 1. So we can calculate our new wealth. That's equal to 1 plus 1 times a half, so that's 1.5. Our new betting fraction, again, is equal to the sum of the previous outcomes divided by the current time step. So it's going to be 2/3. And we have our new bet, which is equal to our betting fraction times our wealth. So in that case, it's 1. Again, that's what's plotted on the slide. So yeah, we kind of carry on playing this game, and let's see what happens. So if we keep going, we keep going, we keep going. Of course, we're for the first few steps of this algorithm, we're seeing the same observation, right? The gradient is always -1, so the outcomes are always 1. So that means we're getting kind of more and more confident in what we're betting, so our betting fraction is going up and up and up, as well as our wealth. Of course, at a certain point, we're going to kind of jump over to the other side of the minimum. And at this point, our outcome, of course, is going to be different, right? So now we observe a -1. And we can calculate each of the kind of quantities of interest here. So our new wealth is going to be this number here. Our betting fraction now goes down from what it was before, because now we've seen something different. And our new bet, in this case, is going to be this number here. So our wealth is massively decreased because we made kind of a very confident bet on the wrong outcome, essentially. Okay, so this seems kind of maybe slightly problematic, but essentially if we keep running this algorithm, we get this kind of behavior. And of course, what did the theory tell us? The theory told us it was the average of the bets that converges to a minimizer. So if you run this for a very long time, this is kind of the behavior you see. You get this very kind of quick convergence to somewhere near the minimum, and then you essentially bounce back to the other side, and then so on and so forth. And kind of in the long run, you see that the average of these bets does indeed converge to the minimizer. So that's kind of what this algorithm looks like in practice for a very simple example. Okay, so that's kind of a brief overview of some optimization methods on Euclidean spaces, and in particular of this kind of slightly strange coin betting algorithm, which we can use to remove the dependence on learning rates. Okay, so now we're going to move to optimization on the Wasserstein space. So this is a problem we actually care about, right? So as I said earlier, this is kind of the form of the sampling problem. We want to find the minimizer of this dissimilarity functional f, which is minimized at our target. And analogous to the Euclidean case, to solve this, the kind of standard approach is going to be to kind of try and consider a gradient flow of f over this space of probability measures. So how are we going to do this? We've heard a little bit about Wasserstein gradient flows in a few talks this week, and I'm going to run through maybe a few more of the details behind kind of how you construct these things. So first of all, we're going to need some kind of suitable notion of distance on our space of probability measures. And the choice we're going to make here is the Wasserstein 2 distance. So again, this is probably something everyone is very familiar with, but this is just the infimum over all possible couplings of mu and nu, and then we integrate the square difference between x and y with respect to those those couplings. This is one choice out of many possible choices, but it turns out it's a very convenient choice, and as I said earlier, it kind of leads to many algorithms that people are very familiar with. So it turns out this is indeed a metric space of probability measures, and this is what we call the Wasserstein space. So the Wasserstein space precisely is the space of twice integrable probability measures equipped with this Wasserstein 2 metric. Okay, so this space actually resembles a Riemannian manifold. It's not technically a Riemannian manifold, but it resembles one. So in particular, for each mu in this space, we have a tangent space, and we can equip that tangent space with an inner product. And the inner product is just kind of the usual inner product from L2. So particularly, if you're taking the inner product of two functions f and g, you just take the inner product of them in Rd and integrate with respect to mu. So we can kind of think of this Wasserstein space as kind of a Riemannian manifold in some sense. Okay, and we can move around this manifold using transport maps. So again, just kind of a basic definition here to recall the definition of the push forward. If we have some measure mu in P2RD and we have some measurable map T, the push forward is defined just by this relation here. And the key point I want to say here is that it's fairly straightforward to show that if mu belongs to our Wasserstein space, then so too does the push forward of mu under T. And so that's what I mean when I say we can kind of move around this space using these transport maps. Essentially, if you take the push forward of a measure mu under T, and T is measurable, then the push forward of mu under T is indeed still in this space. The other thing we're going to need is this notion of an optimal transport map. So the optimal transport map between two measures mu and nu in our Wasserstein space is essentially a transport map such that, well, firstly, it pushes mu to nu, and secondly, this is essentially the map which kind of realizes the infimum in the Wasserstein distance. So it's in some sense the optimal coupling between the two measures mu and nu. Okay, so using this optimal transport map, we can actually define some notion of geodesics on this space. And this technically is how we define the geodesic. We essentially kind of introduce this parameter eta, and essentially you kind of move smoothly between mu and nu according to this relation here. And just a key point I want to make here is that this differs from the mixture path between mu and nu. And here's kind of just a little animation just to show that here. So on the left-hand side, we're going to see kind of the Wasserstein geodesic interpolation between two Gaussians. And on the right-hand side, we're going to kind of see the mixture interpolation. And essentially, at the level of kind of, if we were using particles to represent our distributions, essentially the geodesic interpolation will never kind of transport particles. So kind of pushes them smoothly between the source and the target, whereas this mixture interpolation essentially allows us to kind of transport mass. Okay, so now we have this optimal transport map. We can actually also now define some notion of convexity on this space. And this looks, right, very similar to kind of how we might define convexity in the Euclidean case. It just requires this kind of notion of the Wasserstein geodesic between mu and nu, but otherwise this is kind of the very natural kind of analog of how we define geodesic convexity in the Euclidean case. And one remark to make here is that the nice thing is that the functional f, if we define f as the KL divergence, it actually inherits a lot of properties from essentially the potential function in the measure we want to sample from. So in particular, if we want to sample from some pi which is proportional to e to the minus mu, some potential function mu, if mu is m strongly convex, then it actually turns out that the KL divergence between mu and pi is m strongly geodesically convex in our Wasserstein space. So here's kind of nice. So we can kind of inherit properties from whatever our potential function is into the Wasserstein space. Okay, so we've had a lot of definitions. The final one we're going to need is some appropriate notion of the gradient on our space. Of course, if we want to define a gradient flow, we're going to need some notion of the gradient. And again, it looks slightly technical, but you can essentially view this as kind of the natural kind of Taylor expansion on this Wasserstein space. So in particular, we're going to kind of consider a perturbation on the Wasserstein space. So we're going to take some function h in L2, we're going to take some small epsilon, and we're going to consider the push forward of mu under the identity plus epsilon times h. So as I said earlier, this is still going to belong to our Wasserstein space. Then if we look at essentially the kind of Taylor expansion of f evaluated at this thing, we're just going to identify the Wasserstein gradient as the kind of the term which appears, the first order term which appears in this expansion. And this essentially is going to be a vector field which belongs to L2 of mu. Okay, so just a quick example to kind of bring this back home a little bit. If f is our KL divergence, in this case you can show that the Wasserstein gradient is just equal to grad log of mu over pi. And so to make this even more concrete, let's suppose that our target pi is Gaussian and our mu is also Gaussian. Then if we substitute that into the above, we get this kind of form for our Wasserstein gradient. So we can actually plot what this looks like, of course. So here, if we just have pi in blue being the target and mu being our kind of current density, in red we show kind of what the Wasserstein gradient looks like evaluated at these different values of x. So kind of pushing us back towards pi. Okay, so finally we've got now a notion of gradient. How do we define a Wasserstein gradient flow? Again, we've seen this before in other talks. This is how precisely we can define a Wasserstein gradient flow. It's essentially a solution of the continuity equation, which I'm sure many people will be familiar with, in the case that the kind of driving velocity field Vt is set equal to the negative of the Wasserstein gradient. Okay, so how are we to interpret this PDE? Well, if we define some particle x, which is the solution of this ODE down here. So in particular, the time derivative of x is equal to the negative gradient of our functional evaluated at x, and we initialize this ODE at mu naught, then it turns out that the Wasserstein gradient flow precisely describes the evolution of the density of x, which evolves according to this ODE. So that's kind of how to conceptualize what this kind of equation is doing, which is at the level of a density, at the level of a particle, which is evolving according to the negative of the Wasserstein gradient. Okay, so just to give a very brief proposition which shows that this is essentially analogous to kind of a gradient flow in the Euclidean setting, the value of the objective function f is indeed non-increasing along the Wasserstein gradient flow, and you can show this in a couple of lines. Essentially use the chain rule, and then you substitute in kind of the form of the vector field, and you see that you get this kind of minus square of the Wasserstein gradient, which of course is negative, is non-negative. So this thing is indeed non-increasing along the gradient flow. Okay, so if we go back to our example from before, we substitute in our KL divergence and we substitute in the form of the Wasserstein gradient of that thing, this is what the gradient flow looks like. So that's at the level of the density, and this is what it looks like at the level of the particle. So of course this thing describes kind of a this is an infinite dimensional object, right? This is a PDE, and we're going to have to deal with that at some point. But just again to kind of continue our example, in this special case where our source measure mu naught and our target pi are both Gaussian, then actually this thing reduces to essentially two ordinary differential equations, one for the mean and one for the variance. Because essentially you can show that if the initial measure is Gaussian and the target is Gaussian, then mu t remains Gaussian for all t. So again, just a brief illustration of what the Wasserstein gradient flow looks like in this example. We kind of start over here and we kind of process over towards our target. And again, the blue arrows here are showing kind of the Wasserstein gradient at each of those x's. Okay, so getting back to kind of our main focus here, of course, this is all very nice, this is all well and good, but of course for computational reasons, again, we're going to have to discretize in time. And essentially there are analogs of everything we saw in the Euclidean setting. So you can use kind of a backward Euler discretization that leads to what's known as the JKO scheme. You can use a forward Euler, and that leads to kind of something which maybe would be referred to as Wasserstein gradient descent. There are various other choices as well, and just one to mention, if you consider what's known as a forward flow discretization, which essentially performs a forward Euler step for kind of for part of your discretization, essentially a splitting scheme, which does kind of a forward Euler step followed by an exact solve. Then you get the unadjusted Langevin algorithm. Okay, and as I kind of mentioned right at the top of the talk, considering different discretizations or considering different ways to approximate the terms in these discretizations leads to various different algorithms which have been studied in the literature. So SVGD, which I showed kind of animations from earlier, maximum mean discrepancy descent, Kernel-Stein discrepancy descent, and some other schemes as well. Essentially, you get to these by either introducing different approximations into kind of the underlying equations or changing your choice of functional. So you end up with all these schemes via the viewpoint of this problem as an optimization problem. Coming back to our central point, naturally the convergence properties of all of these schemes is going to depend on the choice of step size. And essentially what we're going to do, and this is probably not going to be a surprise at this point, is we're going to essentially obtain kind of a step size free approach by extending this kind of slightly strange coin betting construction we saw earlier to the space of probability measures. So it's going to be exactly the same setup as before. Everything essentially is the same now. Apart from we're going to have a slightly different bet now. We're going to bet xt minus x naught for some initial x naught. Other than that, everything is the same. And we're now also going to assume that our initial x naught has some distribution mu naught. Again, everything else is the same here. And putting everything together, that gives us this scheme, which again looks very similar to before, apart from everything essentially is shifted by this x naught. So this defines a sequence of x's, and we're just going to define a sequence of measures as the law of these x's, which essentially is the push forward of the law of x naught under this transformation. Okay, so how do we go from this to a sampling algorithm? Well, again, we play the same trick as before. So we're going to set the outcomes of this kind of betting experiment equal to the negative Wasserstein gradient, substitute that in, and the hope is that we're going to end up with kind of a sampling algorithm. And this is what we're going to call coin sampling or coin Wasserstein gradient descent. Similar to the Euclidean setting, you can actually show that this thing does give you something sensible. So particularly under some conditions, so particularly we need f to be geodesically convex, and we also assume some bound on the Wasserstein gradients. Then if you have some additional technical addition, which I'm not going to go into now, then you get this rather ugly looking bound. But again, what's the takeaway here? The takeaway here is that this thing scales as 1 over root t up to some additional logarithmic factors. So this thing is indeed converging to the target. Okay, so we might be asking, is there a simpler approach than this? This coin betting construction is kind of nice, it's kind of powerful, it's kind of interesting just because it's very different to other algorithms, but is there something simpler which looks more akin to, I don't know, gradient descent with some kind of adaptively set learning rate? And the answer is yes. So let's go back to our kind of original Wasserstein gradient descent algorithm. So essentially this looks like this. We essentially push forward the measure at each time step by minus the identity minus the step size times our negative Wasserstein gradient. If we suppose that f is geodesically convex, you can actually bound the error of the average iterate as using this upper bound. I won't go into the details of this, but you can kind of derive this upper bound. And we can now play a game which is, let's minimize this thing on the right hand side with respect to gamma, right? Let's find the kind of best worst case learning rate. And if we play that game, you find that the optimal learning rate is given by this here. So it's equal to the Wasserstein distance between mu naught and pi divided by the square root of the sum of the Wasserstein gradients. And if you substitute this into our previous inequality, you essentially get this as kind of a worst case optimal error bound. So this might be reminiscent of the error bound I gave in the Euclidean case, and again, that shouldn't be too surprising. So this thing now scales as kind of 1 over root t, and it also has dependence on these kind of other problem parameters. Okay, so of course, as I said right at the top of the talk, it's all very well and good. We can kind of derive this so-called optimal learning rate, but we can't compute this thing, right? Because it depends, firstly, on the Wasserstein distance between mu naught and pi, and also it depends, if you look at the sum here, this actually sums up to capital T minus 1, where capital T is the assumed total number of iterations. So in other words, this is kind of assuming we can observe all the gradients in advance, which of course we can't. So we're gonna do two things. One is we're just going to replace the distance on the top between mu naught and pi by essentially a running distance between mu naught and our current iterate. And you can kind of see the logic for that, which is that if mu t does indeed converge to pi, then this thing is going to look a bit like what we had in our original optimal learning rate. And then on the bottom, we're going to do the natural thing, which is just replace that sum up to capital T minus 1 with the sum of the gradients that we've seen so far. And I'm going to refer to this scheme as Wasserstein distance over gradients, or WDOG. The reason being, of course, we have a Wasserstein distance over some gradients. Okay, and just a brief theorem, but I won't spend too long on this. What can we show? Well, under kind of similar assumptions to before, we can again show that kind of a weighted average of the iterates, the distance between f evaluated that and f evaluated the target, converges at a rate of 1 over root t with some additional logarithmic dependence on other problem parameters. Okay, so a couple more points to make. These are now our kind of two update equations. The problem we have still is that these updates depend on the unknown sequence of measures, right? So what are we going to do? Well, we're going to play a couple of tricks which are kind of very familiar to people who have worked on kind of particle-based methods or particle-based variational inference like SVGD. The first is we're essentially going to replace kind of these measures with a kind of empirical measure of n interacting particles. So we're going to iterate a kind of set of capital N particles according to these update equations, and then we're going to replace our mu t in these equations with this empirical measure. So that kind of solves problem one. Problem two is that if we want to use the KL divergence as our objective functional, then the Wasserstein gradient of this thing is ill-defined when mu is a discrete measure, which it will be if we're using this kind of interacting approximation of particles. So what we're going to do, and this is a trick that originates from SVGD, is we're going to replace our Wasserstein gradient by kind of a kernel smoothed version. So we're going to introduce some kernel k, and we're just going to smooth our Wasserstein gradient by integrating with respect to this kernel. And you can actually show quite rigorously, and this is from a paper by Nick Nuskin and Andrew Duncan and others, that this precisely plays the role of the gradient in the RKHS defined by k. So this is still a gradient in some sense, but it's just a gradient in kind of a slightly different space with a slightly different geometry. Okay, and the key point here is that if we use integration by parts, and we do indeed kind of smooth this Wasserstein gradient using this kernel, we can use the kind of standard trick, and you end up with this expression here, which is now just an expectation with respect to mu. So in particular, you can just, if we're using this kind of empirical measure, this thing just reduces to a sum over the particles. Okay, so now we have essentially these two update equations, which might look a little bit horrible, but they are actually easily implementable. Yeah, these things you can actually indeed run in practice. Okay. So just to mention a couple of extensions, based on kind of the connection I talked about earlier, various other problems being amenable to this viewpoint as being optimization problems on this space of measures, you can actually use similar approaches to obtain learning rate-free sampling algorithms for sampling firstly in constrained domains, so this is a slightly more challenging problem, and also for learning rate-free maximum likelihood trading of latent variable models. Okay, so I'm just going to spend maybe 5 or so minutes running through a few numerics just to show that this thing does indeed do something sensible. So here's just a few kind of toy examples in 2D where we're kind of comparing the performance of, or the final samples generated by this kind of coin SVGD and SVGD. And you can see in all these cases it is doing something sensible. Even in cases where we kind of don't have this assumption of geodesic convexity. And just to kind of show a couple more of these animations, just because I quite like them. Again, this is similar to the animation we saw before, which is that if you choose the learning rate poorly for SVGD, you get either kind of an explosion or you get this kind of very slow convergence to the target. Our method, of course, without a learning rate or step size, avoids this problem entirely. Maybe just one more of these. So again, a different target, and you kind of see a similar thing here. Okay, so let's make this a little bit more quantitative. Here you can see kind of just essentially showing the sample quality as a function of the number of iterations. So how are we measuring sample quality here? We're using the KSD. And you can see in particular that both DOG or WDOG SVG and coin SVGD converge very quickly, similar to kind of the convergence of SVGD with kind of a large learning rate. And in fact, in these examples, essentially, if you try to match the convergence rate for SVGD with our algorithms, you can kind of keep pushing up the learning rate higher and higher until you can kind of converge as quickly, but you end up converging very quickly and then having this kind of ongoing bias or kind of this error in the final approximation. Okay, so one other interesting plot here, which is kind of to just showcase another benefit of these algorithms. It turns out that for certain targets, the optimal step size to use for this SVGD algorithm actually depends on the number of particles you want to use to approximate your target. And this is kind of important because you can imagine a scenario where you run SVGD with a very small number of particles over a kind of a grid of different step sizes to try and tune your learning rate, and then for your kind of final inference you use a much greater number of particles to get a better kind of approximation of your target. But it turns out that wouldn't be a sensible thing to do, because the optimal learning rate actually depends on the number of particles you're using, and this is what this plot is showing. In the blue, this is SVGD, where we've kind of tuned the learning rate for a small value of n, and then we've run the algorithm using different numbers of n. And you can see in that case the approximation quality is much worse than if you were to either run SVGD where you were to tune the learning rate each time you change the number of particles, or if you were to use kind of our algorithm. So again, our algorithm kind of bypasses that problem entirely. Okay, so this is just showing this thing works for constrained targets as well. So this is a sparse Dirichlet target and a quadratic target, both in this case defined on the probability simplex. And what we're showing here is kind of the approximation quality as a function of the learning rate. So in the case of kind of our coin algorithm, which is shown in blue, obviously this thing doesn't have a learning rate, so that's why you see this flat line. And what you essentially see is that other algorithms, such as these essentially adapted versions of SVGD, which are suitable for constrained targets, shown in the green and the red, these will do slightly better than our method if you find the optimal learning rate, but generally if you're outside kind of a very small range of learning rates, you're going to perform worse. Okay, so just a few more, I guess, examples to this effect. This is kind of in now a Bayesian logistic regression example with kind of a large data set. So in this case, we kind of need to use data subsampling. And again, you can kind of see the performance of these methods essentially matches the optimal performance of kind of existing methods, so SVGD in this case, without the need to do this learning rate tuning. So again, on the left-hand side, you kind of have the performance as a function of the learning rate, and on the right-hand side as a function of the number of iterations. Okay, I'm just going to show maybe one more example before I wrap things up. This is a slightly different setting now. So in this example, we were looking at this, what's known as post-selection inference or selective inference, and I can't claim to be an expert at this, but the idea here is that you're fitting some model and you're using something like the lasso or the randomized lasso, and what that means is if you try and form classical confidence intervals for the coefficients which are included in your final model, those are going to be invalid because essentially you've used the data to choose which variables are going to be included in your model. So that kind of violates the assumption that your model is independent of your data. So post-selection inference essentially conditions on the initial model selection and allows you to construct valid confidence intervals. And essentially you can show that this boils down to a constrained sampling problem. And so on the next slide, I'm going to show some results which we were testing our algorithm and comparing it to some other algorithms on the HIV-1 drug resistance data set. So essentially what we're trying to do here is to find mutations, gene mutations, which are associated with resistance to a particular HIV drug. Okay, and here's some results. So these are different kind kind of mutations shown along the x-axis, and these are essentially the estimated coefficients and their confidence intervals. We've got a few different methods going on here. So our method is shown in blue. Then we've got kind of in orange and green are these versions of SVGD which are suitable for constrained targets. Then in purple you've got this kind of gold standard method which works very well but can take a very long time to run. And then finally in red you've got the kind of unadjusted confidence intervals. So this is essentially where you form these confidence intervals naively without accounting for the conditioning on your model selection. And what you can see essentially is our method kind of coincides to a fairly good degree with both these existing methods with a well-tuned step size, which were in orange and green, and with this kind of gold standard method in purple. And in particular, I guess the key thing here is that they all give very different results to kind of the unadjusted setting where you don't adjust for this selection. And just to kind of bring home the message about how important the choice of learning rate is, this is essentially the same plot from before, but where now I'm showing the results for the kind of MSVGD and SVMD methods for poorly chosen learning rates. And you can see in that case, clearly you get very different results to any of the other methods which are clearly suboptimal. Okay, so I'm going to leave things there in terms of examples. This thing works as well on Bayesian neural nets. So just a quick summary. So leveraging ideas from convex optimization, we're able to kind of get learning rate free analogs of several existing particle-based sampling algorithms. There's lots of kind of areas for future work here. There are quite a few remaining gaps between theory and practice. So in particular, we have results for kind of this, the kind of mean field scheme, which is at the level of the measures, but once you introduce these particle approximations, things get much more challenging. There are other questions like, can we develop a learning rate free analog of other kind of more classical MCMC algorithms, things like LMC? Can you establish convergence rates under weaker assumptions and convexity, which we know is violated a lot of the time in practice? And finally, are there other problems which we can kind of view through this lens of optimization on measure spaces? There's a couple of references, and I'll be happy to take any questions.
Out of curiosity, is there any connection between co-investment-based rates and line search approaches?
I would say they are fundamentally different in some sense. I guess line search, you're still typically talking about kind of gradient-based methods, right? And you kind of look at one step ahead and you say, you can kind of try and optimize for the best learning rate to guarantee the biggest descent, say, in your step. So I'd say that is maybe has closer connections with this kind of distance over gradients type approach. But in some sense, the coin betting is kind of an entire different construction. To kind of it doesn't fit within this kind of existing framework of a gradient flow or discretization of gradient flow.
I have a follow-up question.
Yes.
First, thank you very much for the very, very interesting presentation. So in your construction with the coin, you have the gradients at the different stages or the subgradients that come into play, right? And you combine them. And this is a construction that exists in conjugate gradient with the fill-off spaces. Okay. Did you look into that and compare the kind of rates that you can get in similar situations?
I haven't looked at that at all. That sounds very interesting. But it's not something I've looked at. But
so in conjugate gradients, you have the series of gradients at the visited points, and you strive for optimal combinations in these subspaces.
Okay. Okay. Right. That would be interesting to compare to that. Okay. Thank you.
Your summary of the Euclidean scenario, you had the norm between the iterates and the optimal.
Yes.
That affecting the optimal rate.
Yes.
Right? And something similar happens here, I suppose, in the versus time.
Yeah. So I don't know if might take a while to get there. Yes, so I showed the rate, but I think I had made an assumption that the rash sine distance was bounded. So Yes, so you essentially get this rate here. So I've kind of introduced a, I guess, conservative upper bound in this final line, where I'm assuming that the Rastein distance between mu naught and pi is bounded by d. But if you could just sub that in. So you do indeed have the same dependence on kind of the distance between the target pi and the initial motor mu naught.
And does the curvature of the Wasserstein space influence this rate in any way? So it's positively curved for measures on RD, right?
Yeah, it doesn't enter into this, surprisingly. Somehow, yeah, the only dependence is essentially when you kind of write out the math here, you get some kind of telescoping sum. So a lot of the kind of intermediate terms, I guess, disappear, and you end up just with this dependence between mu naught and pi, and everything else kind of in between falls out in some sense.
Extra question by Jeremias, and then we'll move to the break.
Thanks, Louis. It's super interesting. I'm very happy we hired you. And so when you do all these results, it seems like one of the assumptions I don't like that you need is the geodesic convexity stuff, which is really annoying, for example, for Gibbs measures, right? Because it tells you that your loss has to be like strongly convex. Basically, it never is. So is there any hope you can get away from this? I know that this is kind of like common in the sampling literature because it kind of makes sure that you get these like ergodic rates and everything is nice and exponential. But in practice, like when we've worked with these objects, it worked reasonably well without that assumption as well. Is there any way that you can think of that one could get away from that restriction?
The theory, I think, is very challenging in going through, because essentially all the tools you're using to kind of come up with bounds, etc., rely quite heavily on that assumption. As you say, kind of, I mean, it's annoying in terms of what you can say theoretically. In practice, it seems to hold in kind of a much wider range of settings. But closing that gap is obviously would be nice. I think for the coin betting stuff, I'm not sure there's any hope. For the kind of this dog type scheme where it's essentially a gradient descent scheme plus some kind of adaptive way of learning the learning rates, I think there might be interesting things there. There's some work in the optimization literature which essentially comes up with ways to use algorithms designed for convex optimization problems for non-convex problems and come up with theoretical guarantees. So I think potentially if we take some of those tools and use them in this setting, that might be a way forward there. So yeah, for the coin stuff, I don't think so, but for this other stuff, potentially.
So the reason that it wouldn't work for the coin stuff is that basically comes out of this online learning literature where all they have is convex.
It's always convex. Yeah.
Okay, thank you again.